Jnanam paramam dheyam. Knowledge is supreme.
My name is Rama Devi. I am a professor at Department of Physics, IIT Bombay. So, I will be teaching this quantum mechanics course. The tools of quantum mechanics are essential to perceive the microscopic world of atoms and nucleus. The main theme of this quantum mechanics course is to give exposure to Dirac bracket notations. Main emphasis will be on operator formalism and their applications to harmonic oscillator and hydrogen atom spectrum. Every 4 lectures will be followed by a tutorial session by my colleague Dr. Zai More, who will discuss in detail some problems. This will benefit the audience to appreciate the applications of the theory lectures which we will be uploading. We will upload PDF and PPT files of video of every lecture prior, so that these files can be opened for clarity. The references are the first 2 books. The third can be kept as kind of a reference book. It is really a fat book. So, I would consider it to be like a reference book. It has everything, but I prefer the first book to be followed by you, which is Griffiths, and the other book Sakurai will slowly get on to Sakurai also. Shankar, you can use it as kind of a reference. Okay, so this is the plan. I want to take you slowly from what you have learnt in your first year into the second year first course, quantum mechanics. So, there will be review of quantum ideas, then linear vector spaces, operators, state vector formalism of harmonic oscillators. I am going to concentrate on hydrogen atom, angular momentum, then the concept of spin, addition of angular momentum, how does one add to angular momentums. Then these things will force us to introduce a coefficient which is called as a Clebsch-Gordan coefficient. So, we will spend some time in looking at these aspects after. Okay, so this is the main things which will be done. There will be some miscellaneous. Okay, so to start the introduction, why do you want to do quantum? This you have already seen in your first year course, that there are limitations of classical ideas, right. So, what is the first one? You have seen microscopic world, many of the experiments you cannot explain using your familiar Newton's law or any classical law. So, the first thing which you would have seen is the black body spectrum, which is the Planck's law which helped you to fix exactly all the points in the black body spectrum. Is that right? Everybody is with me? And then photoelectric effect cannot be explained just using classical laws. The more intense the beam, more photoelectric current will flow is not correct, right? You all know. So, other thing is the scattering of, which is called as the Compton scattering of photons with electrons, which also you have seen how the wavelength changes. And these things can be explained only using quantum ideas, not classical ideas. So, one of the core important thing which went into all the 3 aspects of quantum aspects of photon, what is that? Is the universal Planck constant. You did not put a constant which was different for black body spectrum. You did not put a different constant for photoelectric effect or a different constant for Compton scattering. Is that right? You all use the same H. It gave you an interesting, that is why it is universal. The same H which you started with, the Planck's constant, which was introduced by Planck to say that the energy of photons are quantized in quantas of integral multiples of h nu. That h is the same h which happens even in photoelectric effect or Compton scattering. Okay, you may be mechanically using it, but it's the universal nature feature which shows up in that Planck's constant, which is called as a Planck's constant H value. Okay, we don't use different values, we use the same value. So, needed introduction of a fundamental constant leading to quantum regime. So, H tending to 0 is a limit where you start getting to the classical physics. Okay. So, H not equal to 0 is the one which we call it as a quantum regime. Okay. So, this is also familiar to you, Planck's equation, E equal to h nu, and you can use Einstein's relativistic energy for massless particle. What is that? E equal to Pc, and you can try and write the momentum of a photon to be h over lambda. Everybody is familiar with this, right? So, for massless photon, E equal to Pc, which is h nu. Is it visible? And from here you can write P equal to h nu by C, which is h by lambda, right. So, this is what the first equation, P equal to Pc, is for the massless Einstein's energy momentum relativistic equation, and Planck's hypothesis is E equal to h nu, from which you can show that the momentum is h over lambda. Okay, so that is what I have written here. So, what was the proposal of de Broglie? He said, why should it be that momentum equal to h over lambda? It should be applicable for other particles as well. That was a daring proposal. He said P equal to h over lambda should be true even for other particles like electron, protons and so on. But E equal to Pc is not correct. But you can write momentum to be h over lambda is the de Broglie hypothesis, which means that there is a wavelength associated with other particles. Treat them as waves. Okay. This P equal to h over lambda is a crucial point which tells you that you can look at any object both as particle. Look at particle, you will talk about momentum. If you look at wave, you will talk about wavelength. And this is an equation which relates both. Okay. So, this is the daring proposal of de Broglie. Equation of wavelength of matter waves must obey the same equations of photon momentum. Okay. So, matter waves, once you start looking at matter waves, you can look at them moving on an orbit and look at the circular orbit with constructive interference, and the constructive interference will give you a condition for a wave as the circumference to be equal to integral multiple of lambda. And once you substitute the de Broglie proposal for lambda, you can also rewrite angular momentum quantization. This is your famous Bohr quantization which you would have read as a proposal. I am just trying to say that once you start taking it as a wave and look at constructive interference on a circular orbit, you automatically get quantization of orbital angular momentum. These are the famous experiments, Davis and Germer, and these show that you can also look at electron beam and diffractions of electron beam, and in that sense it confirms what de Broglie said, that there is a wave nature for particles like electron. Usually when we are given an electron or when we are given a photon, we see photon as an electromagnetic light. We see electron as a point particle. But in this course you should remember that a particle and the wave are part of every object, and what we try to tap is what you will get. Okay. So, depends on the situation. If you are doing photoelectric effect, you will get only the particle nature of photon. If you are doing interference experiments, you will get wave nature of photon. Similarly, electrons, if you are doing collision experiments, in your classical physics, it is like a particle nature, but if you are doing diffraction experiment, it shows the wave nature. Okay. Depending on the experimental setup and its energy, things are going to be different, and that is what is happening in the microscopic world. What we see in our day-to-day life is the macroscopic world. But what is happening inside an atom or inside a proton are governed by quantum ideas. Okay? You can't use your classical ideas and say that what I see here should happen in the microscopic world. We do see violations, that is why we started introducing the quantum ideas. Right? For example, tunneling. I can't just go across this wall outside, but you can still get, if it is a wave, a sound wave could cross across, right? That is, once it's a wave, things can cross. That information can be there in a region where a particle cannot go out, but a wave can go out. Okay? This is your famous experiments which you would have seen, Young double slit experiment, right? And here you have two sources, and if suppose you shut one of the source, you will have this blue line for light coming through S1, similar intensity. Similarly, if I shut S1, you will have a green line due to the light coming through the source S2, the slit S2. But if both are open, okay, what is your expectation? It has to be like a wave. This is what you will expect with constructive destructive interference. But if you try to see which slit through which it went, then what happens? The interference pattern disappears. You will get, if you try to see how, which way it goes, then this is the pattern you will see. So, which way it goes if you are trying to see, then you are looking for the particle nature. Trying to look for the particle nature, it is just the sum of the intensities. If you don't worry about which slit it went through and just look at the screen, it will have a superposition, not intensity adding, it is the amplitude added and then mod squared of it, and you will get an interference pattern. Okay. So, this is the experimental data. They have tried to find out by closely putting a kind of detector here to see whether the beam is coming through this or coming through that at that instant of time. If they try to do that, then they will get the screen B. They don't try to do that by putting some detectors here disturbing the system, they will get the screen C. So, you can get wave nature. If you want to tap the particle nature, the interference pattern disappears. Okay. So, this it was done even for the electron beam, not only for the photon electromagnetic field. Of course, you could do this, but this is done for the electron beam, and it was proven that it has wave nature besides being a particle. So, attempting which slit the electron came from gives plot B, which is a particle info, and either particle or wave nature can be observed, is what I have tried to give you from this plot. Plot C gives the electron beam, which is the wave info. Okay, so I have slowly got you onto the wave particle duality. That is, how many of you have read Jekyll and Hyde? So, the character is this, the same person seems to have two characters, right? Both the Jekyll character is a very good character and the same similar thing, but here every object seems to have a wave nature and particle nature, but if you try to probe what you want to find, it shows that character. Okay. So, in some sense all of us have both wave character and particle character. Why are our wave character not seen? Do you know why? Wavelength is very, very small, which cannot be measured in the present day. So that's why you don't see the wave character. But if you take an electron whose mass is really small, then the wavelength is a measurable regime. So that's why you can have both wave character, and for everyone it is there, but which is dominant in our case is only the particle character. But wave character needs a measurement of wavelength which is within the experimental regime, and that happens only in the microscopic world. Okay. So all the planets, when you study, you will not do quantum. Why? There's no point. It's really a massive object, and you will do Kepler laws, and it's correct. There is no need to worry about the wave character. So that is what you should appreciate, that just because I'm teaching quantum regime doesn't mean that day-to-day life requires, but there are situations where you have to apply. So wave particle duality. So I'm slowly taking you from classical mechanics. When you do Newton's law, you write all the Newton's law where you don't worry about, you can have simultaneous values for position as well as momentum, right? You do write the first equation or the second equation, S equal to ut plus half gt squared when you write, or half at squared, you know both the position as well as the momentum. Okay, it's not that if you know the position, you don't know the momentum. You can measure the velocity or momentum. So that's why that's a very important point, that x and p can be simultaneously found in your classical laws. Equation is Newton's law. What is your aim in the Newton's law? You determine x as a function of t. Once you have x as a function of t, d by dt will give you momentum. The situation completely changes once you go into the quantum microscopic world and you want quantum mechanics. You cannot determine x is the one which gives you the position. P by de Broglie hypothesis gives you the wave nature. X gives you the particle nature. As I've said, you cannot get both the particle and wave nature simultaneously, right? X, when I say the position of the object, I am looking at it as a particle. When I say momentum of the object, by de Broglie hypothesis, I am seeing the wavelength, which means I am trying to look at the wave nature. But I cannot simultaneously, we have seen in the Young's double slit experiment, if you want the particle info, you try to probe by putting a kind of a detector at the slits to see which slit it went through, but then you lose the interference pattern. But if you don't see which one it went through, you get the interference pattern. You cannot go at which one it went through and the interference pattern. That's not possible. Is that right? So x and p cannot be simultaneously determined is one of the core important things which I have tried motivating from the earlier slides. And this is something which you all mechanically learn in your courses, earlier courses, which is the famous Heisenberg's uncertainty principle, that position and momentum cannot be precisely measured. Is that right? So here the equation is the Newton's law in classical mechanics. In quantum mechanics, the equation which you have to solve is the Schrodinger equation, and the main theme of the Schrodinger equation is to find a solution for a wave function, or it's also called probability amplitude. In one dimension, it is written as psi as a function of x. It can also be dependent on time. It's a complex, in general it can be complex, and whose modulus squared will give you the probability. This is something which you have learnt in your first year. So this is the distinction between classical mechanics and quantum mechanics. Classical mechanics course when you are doing, you will be in this regime. Now quantum mechanics course, you will be in this setting. So the familiar Schrodinger equation, the left hand side I have written is the partial derivative with respect to time, and here the right hand side I have written the energy operator or Hamiltonian we call, which can be rewritten as double derivative of the position. I have written it in one dimension just for simplicity. V is the potential energy which the particle is facing, and we would like to solve this equation to find psi of xt, which is the wave function. Okay. So, that is the theme, this is the equation, and it is a, it is a proposal, this equation. There are some indicative ways in which you can derive it by looking at the electromagnetic wave, and then we propose for a non-trivial potential energy, and that is the Schrodinger equation. And many experimental curves, many experimental data are all explained using this, which means this equation should be accurate, it is correct. Okay. Just like Newton's law, there was no violation when you try to verify many things, same way the Schrodinger equation is also useful. Okay, so just to summarize, I will put it as a flow chart. So, we have seen the dual nature of light. Light is usually a wave, but we can see the particle nature from black body radiation, photoelectric effect and Compton effect. Usually particles are particles, you can look at wave nature of particles, they are called matter waves or de Broglie waves. To explain them, you can look at diffraction experiment, uncertainty principle, and you can also look at as a superposition of various waves to look at the group velocity to see the wave packet. So, these are ways of looking at the wave nature of the particles. And Schrodinger equation is the equation which describes a matter wave, and some of the concepts which you would have already studied as the probability, finding expectation values, or they are also called average values of position, momentum, energy and so on. Okay. So, this is quantum mechanics and we will see this in detail.